actor info. And I'd like to do the enemy first because that's the simplest case. We're going to do this in begin play. Now, Aura enemy doesn't have begin play, which means we're going to need to override that here. And while I'm at it, I'd like to make this a little more organized. I'm going to put comment up here above our interface functions because I know that this belongs to our enemy interface. So I'm going to say enemy interface right here. And I'm going to put a comment below these two that says end enemy interface. That way I know that these are from that interface. And these are public. Begin play is protected, so we'll make a protected section and we'll override begin play down here. So we're going to say virtual void begin play override. Let's generate the definition. We'll get our super call and then we can init ability actor info here. So to do that, we access our ability system component pointer and we call init ability actor info. And we can see that the first input is the owner actor. That will be this. And the avatar actor will also be this. Now, if you like, you can check the pointer first. You can even put an assert, such as check ability system component. You can do that. But if I get a crash on this line, then I know why. It's because the ability system component pointer is null. But I don't expect it to be null because I'm initializing that in the constructor. So something is terribly wrong if I crash accessing this pointer. I'm confident enough to use it without checking. Okay, so that takes care of the enemy. Now for the character, which is going to be a little more complicated, but not much. Let's find our Aura character class, but not much. Let's find our Aura character class, the CPP version. Let's find our Aura character class, the CPP version. And we're going to want to override a couple of functions. I'll just pull up my slide here again and remind myself that this is the case we're concerned with, where the ability system component lives on the player state. We're going to initialize ability actor info in possessed by for the server and on rep player state for the client. So we need to override those functions. So that means I'm going to hit Alt-O or Control-KO on Visual Studio to come into Aura character, and I'm going to override a couple of virtual functions. First, we need possessed by. So virtual void possessed by. And if I right click and go virtual void, ride a couple to come in and hit Alt. So we need to override those functions. So that means I'm going to hit Alt-O. Need to for the case we're concerned with, where the ability system component lives on the player state. We're going to initialize ability actor info in possessed by for the server and on rep player state for the client. So we need to override those functions. So that means I'm going to hit Alt-O or Control-KO on Visual Studio to come into Aura character, and I'm going to override a couple of virtual functions. First, we need possessed by. So virtual void possessed by. And if I right click and go to declaration or use usages, we'll see that this possessed by belongs to the A character class right here. And if I go to character.h and search for possessed by, I can see that it is in the public section. And by the way, notice that we see this comment thing happening here for functions that belong to interfaces. We're actually seeing the comment for parent classes being referred to as interfaces. Now, we could do that too if we want. In fact, if you want to copy the same sort of comment style, you can do that as well. It's up to you. We can say begin interface and end interface. So if you want to use that comment style, feel free. But I wanted to see that possessed by is a public function. And we're also going to want to override virtual void on rep player state. And we can go ahead and generate the definitions for both of these functions. And we can go ahead and generate the definitions for both of these functions. There they are. And if we hit Shift, that allows us to search. We can search for onRep player state. And we see that that one belongs to the pawn class. Here it is, onRep player state. And we see here in the pawn class that this function is also public. So we'll go ahead and override that one. Now that we have these two functions, we can do what we need to do, which is call init ability actor info. So we'll start with possessed by. Now remember, this one's for the server. So I'm going to make a comment so we remember init ability actor info for the server. And remember, we need to access the player state. So I need to call get player state. And we have a template version of this, so we can pass in a Aura player state as the type, and that will return the appropriate type. Now I'm going to make a local Aura player state variable. I'm going to say a Aura player state called Aura player state. And I'm going to wrap this in an if statement. So if, that way, if this is valid, which it should be at this point. In fact, it's kind of important. Let's go ahead and just use an assert instead. This should not be a null pointer. We should be pretty confident. So we'll say check Aura player state. And then we'll take Aura player state, and we're going to get the ability system component from this. We're going to call get ability system component. And from that, we now have the ability system component. We can call init ability actor info. And we can pass in the owner actor and the avatar actor. Now, in this case, the owner actor is going to be the player state. So we're going to pass in Aura player state for the owner actor, and the avatar actor will be the character itself. That's going to be this. So that's the difference when you have the ASC or ability system component on the player state. But we have to set this here in possessed by because we need to be sure that we have a valid player controller set already and that our player state is valid and accessible. And we can call this function here. So that takes care of this. But remember, we have the player state now. That's a good opportunity to set the Aura character's ability system component pointer. So we're going to say ability system component equals, and we'll take Aura player state and call get ability system component. We'll set that, and we'll set our attribute set as well. We'll say attribute set equals Aura player state get attribute set. And now we're starting to see the benefit of having those getter functions. Okay, so these pointers are set here on the server. And we've initialized ability actor info here on the server. We're going to want to initialize it for the client as well. That's why we're doing it in onRep player state, which means we're going to do the very same thing we did here. We're going to get the player state, check it, and call init ability actor info and set these two pointers. We're going to do the same thing. Now, rather than just repeating myself, you may have heard of the DRY principle, DRY, don't repeat yourself. Rather than copying several lines of code and pasting them, I would like to instead create a function that I can reuse in both of these. So let's go ahead and go to Aura character here and make a private function that we can just call twice. So I'm going to say void, and I'll just call this init ability actor info. That's really all it's doing. So let's make a function definition, and it's going to be these lines of code here. So I'm going to go ahead and Control X and Control V. Now we have a function that does these things for us. We can call it here in possessed by, and we can call it here in on rep player state, and we'll have a comment here that says init ability actor info for the client. And that's it. Now, if you didn't do this refactor into a function, that's totally fine. It's okay if you repeated yourself, not a big deal. I do recommend making a function, but you don't have to. And now we've achieved a couple things. For one, our ability system components know who their owner is. They know who the owner actor is, and they know who the avatar actor is. That's going to be very, very useful and convenient as we continue programming in GAS throughout this course, because there will be many, many times when we need to access those owners. in our abilities, in our various gas classes. So this is a very important and crucial step. And before we end the video, I'm going to bring your attention back to the replication mode again. Remember, we set our ability system component for the player-controlled character to mixed replication mode. And it's important to know a couple of details when you do this. For mixed replication mode, it's important to know that the owner actor's owner must be the controller. Now, in our case, the owner actor for our ability system component, at least for the player-controlled character that has mixed replication mode, is the player state. That's what we set as the owner actor in init ability actor info. Now, we don't need to set the player state's owner to the controller because that's what happens by default. The player state's owner is automatically set to the controller. So we don't really need to do anything. Similarly, for pawns, this is automatically set in possessed by. So if the owner actor for the ability system component is the pawn, well, in possessed by, the pawn's owner will be set to the controller. But if your owner actor is not the player state and you're using mixed replication mode, you must call set owner on the owner actor and set its owner to the controller. So even though we don't need to worry about it because our owner actor is the player state and the player state's owner is already set to the controller, you need to know this because your owner actor may be some class that does not automatically get its owner set to the controller. In that case, you're going to want to make sure that it is, if applicable. You might have an ability system component on some actor that doesn't have a controller. In that case, that's fine. Don't worry about it. But for mixed replication mode, the owner actor's owner must be the controller. So keep this in mind. This is not something that you'll worry about in this course, in this project, but keep it in mind for your future gas projects where things might be different. So just something you might want to jot down. Okay, excellent job. We'll continue with this in the Welcome. Now, we've just put a lot of effort into adding an ability system component and an attribute set. We were careful to initialize our ability component and an attribute set. We were careful to initialize our ability system component with an owner actor and an avatar actor. So our ability system component knows who its owner is. What about the attribute set? Well, when we construct the attribute set alongside the ability system component inside the owner actor's constructor, as we've done, it's automatically registered with the ability system component. The ability system component has access to it, and any other attribute sets that are registered with it. We can have multiple attribute sets if we wish. Say you want to distribute your attributes among several different attribute sets based on category. Well, you can do this if you like, but it's important to know that each of these must be separate classes. You can't have more than one attribute set of the same class type. Otherwise, you get ambiguity attempting to retrieve it from the ability system component. On the other hand, it's perfectly acceptable to contain all of your attributes on the same attribute set. This can make things simpler, especially if the attribute set needs to know about the values of the other attributes when making calculations. Attributes take up negligible memory, so you can even share a single attribute set among all classes in your project if you wish, and simply use the attributes that you need in any given class. In this game project, our attribute set will contain attributes that are used by all characters in the game, so we'll have just a single attribute set, but keep in mind for future reference that you can have multiple. So what are attributes exactly? Attributes are numerical quantities associated with a given entity in the game, such as a character. All attributes are floats. They exist within a structure called gameplay attribute data. Attributes are stored on the attribute set, and the attribute set keeps them under close supervision. We can know when an attribute changes and respond to it with any functionality that we like. Now, attribute values can be set directly in code, but the preferred way to change them is by applying gameplay effects. When we get to gameplay effects in this course, we'll soon learn that gameplay effects can change attribute values in a number of different ways. Aside from the built-in capabilities of gameplay effects, another reason to use them is because gameplay effects allow us to predict changes to attributes. Prediction means that the client doesn't need to wait for the server's permission to change a value. The value can change immediately client side, and the server is informed of the change. The server can then roll back any changes that it deems invalid. This is a huge benefit because prediction can take a lot of extra work to program yourself. Prediction is something that makes for a smoother experience in multiplayer. It's one of those things that you don't notice when it's there, but you do notice when it's not. Here's how a client-side change would occur without prediction. On the client, let's say you have an attribute that needs to change. Since the server should be in charge of important gameplay changes, otherwise clients would be able to cheat, a request is sent to the server telling it that the attribute's value needs to change. So the server receives the request, decides whether that request is valid based on any number of criteria set by the developers, and if that change is deemed valid, the server then sends the confirmation back down to the client, who can now change the attribute's value. Since data takes time to travel across the network, this results in a noticeable delay from the time the client needed to change the value to the time it received permission from the server to actually change it. It's not unusual for lag times to reach 100 milliseconds or more. So performing an action in the game and having a noticeable delay before you can see and hear the effects of that action makes for a very bad gameplay experience. Let's see how this type of thing works with prediction. With prediction in GAS, a gameplay effect modifies an attribute client side, and that change is perceived on the client instantly. No lag times. Then that change is sent up to the server. Client instant modifies an attribute client side, and that change is perceived on the client instantly. No lag times. Then that change is sent up to the server, who still has the responsibility of validating that change. If the server decides it's a valid change, then cool. It can inform the other clients of the change. However, if the server decides that the change is not valid, let's say a client hacks the game and tries to do an ungodly amount of damage, for example, then the server can reject that change and roll back the changes, setting the client's value back to the correct one. So the server still has authority, but our client doesn't have to have a delay. Prediction is complicated, and having it as a built-in feature throughout GAS is a huge benefit that lets us focus on creating gameplay mechanics and not worry about implementing lag compensation. So an attribute is an object of type F gameplay attribute data, and is stored on the attribute set. Attributes actually consist of two values, a base value and a current value. The base value is the permanent value of an attribute. The current value is the base value plus any temporary modifications caused by gameplay effects. Think about this in terms of buffs and debuffs. You may have an effect that adds or subtracts a value for a certain period of time, and once that time is up, that modification is undone, and the attribute goes back to its base value. Now, you may be tempted to conclude that the base value is the max value for the attribute. For example, when calculating the percentage for a health bar, do you divide the current value by the base value? Well, no, this is a common mistake, and it's not the way to go about it. The max value for an attribute is separate from the attribute itself. If the max value can change, which is pretty common, the max value should be its own separate attribute. This way, we can have gameplay effects applied to the attribute itself or applied to the max attribute separately. And the percentage for your health bar, for example, can simply be the fraction of health divided by max health. So now that we know what attributes are, it's time to add some to our attributes set, and we'll do that next. Okay, we're ready to add some attributes to our attribute set. So I'd like to close all my tabs. I'm going to right-click, close all tabs, and I'm going to get my attribute set. I'd like to get the header file open here. So I'm opening Ability System, and here's my Aura attribute set. Now it's pretty empty, and I would like a public section along with a constructor. So I'll add the public section, I'll declare the constructor, and I'll go ahead and generate the definition for it. That's going to open my CPP file. All right, great. Now back to the attribute set. We're going to declare our attributes right here in the public section. And I think the first attribute that's essential to just about any RPG character is health. Now, whether you call it health or life, it doesn't really matter as long as you pick a convention and stick with it for the game project. Since health is pretty universal, I'm going to use that. Now, we know that attributes have the type f gameplay attribute data. So we're going to make a variable of that type and call it health. So that's the first thing we need to do is create the variable. But there are just a couple of other things we need to do when we create an attribute. And these are the steps that you'll be taking when you create all of your attributes in all of your GAS projects. Now, we're going to make this a uProperty. And we're also going to make this a replicated variable. Most of our attributes are going to be replicated. There will be a couple of exceptions, and we'll get to those. But we want our variable to be replicated to all clients. So if it changes on the server, then clients will get the updated value. And if we change it via gameplay effects, we know those are predicted, which means that they'll be changed locally on a client, and the server will be informed of that. And so the server can change it. And once it changes on the server, all other clients need to know about that change. So it's important that health is replicated. So to make a variable replicated, we mark it replicated with the replicated specifier. But for an attribute, we need to use a rep notify. Remember, rep notifies are called automatically when a variable replicates. So when the server replicates the variable down to a client will have the rep notify for that variable triggered as a result. So we want a rep notify for health, and to do that, we use the specifier replicated using equals, followed by the name of the rep notify. And a common Unreal Engine convention is to create a function called onRep underscore followed by the variable name. So we haven't created this function, it doesn't exist, but this is how we mark health to be replicated using a rep notify with that function name. So we have to create that. We have to make a void function called onRep health. And in order for it to be a rep notify, it has to be a U function. Now, rep notifies can take 0 arguments, or they can take 1 argument. And if they take an argument, it has to be of the type of the replicated variable. In other words, an f gameplay attribute data. It can be a const reference for this. And if we provide that input parameter, then when onRep health is called in response to health being replicated, then it will get the old value passed in as an input parameter. And this is useful for comparing the new value with the old value. So we're going to add a const f gameplay attribute data reference, and this will be called old health. So we can generate the definition for this, and as you can see, we have this old health here. So when health replicates, it will now be equal to its new replicated value, but we still know the old value because it's being passed in here. And this is just an inherent quality of rep notifies. If you add that input parameter, then you get the old value, and that's useful. Now, when we set up the rep notify for a replicated attribute in an attribute set, we have to inform the ability system of that change so the ability system can do all the under the hood bookkeeping that it needs to do to keep the ability system together, working cohesively. And to do that, we use the macro gameplay attribute underscore rep notify. And this requires the class name, and that's going to be this class, the Aura attribute set. We're going to pass in that, followed by the name of the replicated attribute, that's going to be health, followed by the old value, which is old health. So we'll pass in the old health value as well. And now the gameplay ability system will know that health has just been replicated. Now we're going to need to include ability system component to get rid of that red squiggle. So I'm going to go ahead and include that header, ability system component.h. And writer is going to be telling us that we can make this function const if we want to. And of course, to do that, we would just add const there. but we'd have to add it here as well, const. So this takes care of informing the ability system that we're replicating a value, that its value has just come down from the server and changed. And now the ability system can register that change and keep track of its old value just in case anything needs to be rolled back. Remember, in the case of prediction, the server can roll changes back and undo them if it deems that those are not valid changes. Okay, so that's almost everything. But if you've taken my multiplayer course, you know that to mark a variable as replicated, there's another step we need to do. There's a specific function that classes must have in order to register variables for replication. And that function belongs here, just under the constructor in the public section. It's a virtual function, it's void, and it's called getLifetimeReplicated props. And getLifetimeReplicated has an input parameter of type TArray holding f lifetime property. This TArray is a reference, and it's called out lifetime props. This is a const function, and we're overriding it. So kind of a long function signature there, but this is the function we must override to replicate any variables. And if we go ahead and generate the definition for it, then this is the place where we register variables for replication. And to do that, we use doRepLifetime. Now, doRepLifetime has a number of flavors, one of which is condition notify. That's the one we use for replicated attributes. This requires the class name, or a attribute set. It requires the variable itself, that's health. Next is a condition, and if we type cond_, we'll see that we have a number of conditions. Now, you don't need to know a whole lot about this system to do this course. You just need to know about the one we're using here. We're going to use condition none. In other words, we don't want to set any conditions for this variable to replicate. We always want to replicate it. And finally, we can add one more option, repNotify always. Now, let me just explain what this line is doing here for a moment. It's registering health to be replicated. That's required for anything that you would like to replicate. It's going to replicate without any conditions, and there are other conditions you could set. For instance, if you wanted to only replicate to the owner, there's an option for that, but we don't want any conditions, so we're setting it to none. And repNotify always means that if the value is set on the server, replicate it, and on the client, that value will be updated and set. Now compare that to onChanged, which is the default option. With onChanged, if you set the value of health on the server, and that value hasn't changed, then there will be no replication. This is a sort of optimization. If you're setting it to the same value that it already has, there's no need to replicate it in most cases. But for Gas, we want to replicate it anyway. Because if we're setting it, we may want to respond to the act of setting it. Whether we've set it to a new value or its own same value, you may want to respond anyway, even if its numerical value hasn't changed. And for that reason, we use always. So that is the last step to creating an attribute. And the attribute is set to replicate with a repNotify, but that doesn't mean we can't have additional uProperty specifiers. You might want this to be accessible in Blueprint, so we can make this Blueprint read-only. I typically like to, in case I'd like to access these from Blueprint, and I typically give them a category as well. And this is going to be a specific type of attribute. It's related to the well-being of the character, right? It's the character's health. So we can refer to these as anything we like. I'm going to call these health and other associated attributes vital attributes. Okay, so now that we have health, let's do this process one more time together, and then I'm going to set you loose to do it on your own with some additional attributes. So we'll do this one more time, and when we create health, we typically like to create a max health attribute. So I'd like to do this for max health as well. So I'm going to create an f gameplay attribute data called max health. And I'll give it the same uProperty, just about the same, with one key difference. Its repNotify has to be different. We need a repNotify for max health. So we'll create a void function on rep_max health. And it's going to take a const f gameplay attribute data reference, only it's going to be called old max health. And it'll be const, why not? And we can generate its definition, and it's going to need the gameplay attribute repNotify. I can copy and paste it. Instead of old health, we pass in old that the repNotify needs to be registering max health and get lifetime max health. Adding a new attribute involved. You create a repNotify that can accept the old value. You define that repNotify and add the boilerplate gameplay attribute repNotify macro to it. And then you add that replicated variable to get lifetime replicated props with condition none and repNotify always. Now we refer to all these steps as boilerplate. Boilerplate is just a required number of steps to get something set up and working, and with attributes in the attribute set, it's very much boilerplate. You're going to do this for all of your Gas projects. Anything that requires that you have attributes, you've got these boilerplate steps to follow. So now that we've done this a couple times, you should feel pretty confident being able to do this on your own. So I'm going to give this to you, student. being able to do this on your own. So I'm going to give this to you as a quest to do this. So yes, project attribute set, number of steps, boilerplate. Boilerplate is to get lifetime replicated props with, and go through all that copying and pasting here. I'm going to copy both of these and paste. Them, and I know that this will be, and looking at sing rep max, you might have noticed that. So that should be on rep max health for the max health variable. Mana should be on rep mana, and max mana should be on rep max mana. And these can be the vital attributes. Okay, good thing I caught that. That would have been a bug waiting to happen, right? And I can go ahead and duplicate these two functions as well and change them to mana and max mana. So this one will be on mana, and it will take old max mana, there we go, both of them, and old mana and old max mana. Now, the last step, and I actually forgot this when I initially recorded this video, is to register props. Easily miss one. Well, don't do what I did. Make a notify here. So I'm going to copy and max mana. Replication. In future videos, if you see that these two lines are not there, don't go and remove them. It will not. You should have them. They'll be missing here, like I did, and change what you need if you copy and paste. But if you're careful, you can save some time that way. That's the thing with these engineering new attributes on Forge system, that we have our attribute set, and that's great. So great job. I'll see you in the next video. Welcome back. So now that we have 4 new attributes in our attribute set, we're going to learn how to easily create some accessor functions to retrieve and set these, even though usually we don't set these from code directly. We use gameplay effects, but we haven't learned about gameplay effects just yet. So we do need to know that we can, in fact, set these from code with regular old setters. Now for getters and setters, there exist some pretty handy macros that make it easy to mutate and access these attributes. And I'm just going to show you one for health. Just under health, I'm going to use the gas-specific macro gameplay attribute underscore property getter. Now this requires 2 inputs, the class name, which is Aura attribute set, of course, and the property name, which is health. So what exactly happens when we call this? Well, let's go ahead and just jump to its definition. I'm going to right click here in Writer. It's go to declaration or usages. You can just peek the definition in Visual Studio. But here it is, gameplay attribute property getter. It's a macro. It's defined right here. In fact, here in attribute set, this big comment explains it. It says this defines a set of helper functions for accessing and initializing attributes. To avoid having to manually write these functions, it would create the following functions for attribute health. It uses health as the example. It says that these macros result in creating get health, which is a const getter, set health, which does what you'd think a set health function would do, and init health, which initializes the health. It says to use this in your game, you can define something like this and then add game-specific functions as necessary. And it says here, define this macro called attribute accessors. If you define this, then when you call attribute accessors, it will call these 4 macros, which create the getter for the attribute, the getter for the value, the setter for the attribute, and the emitter for the attribute. And why do we have get health attribute and get health? Well, that's because the attribute itself is its own type, fGameplay attribute. That's the attribute that fGameplay attribute data contains within. And get health would return just the float. You can see it returns float here. So one returns the actual attribute object, the other returns the numerical value of health. See the difference? So we can take a look at these macros. It's not imperative that we understand the macros. This is macro creation magic. This macro here is generating a new function called get property attribute. So it's using macro magic to generate a getter function for us. And I'd just like to point out one quick difference between set and init. You see, set is going to set the numeric attribute base, that's the base value for the attribute, whereas init sets the base value, but also sets the current value, base and current. It's basically saying start off with the same base and current value, which is what we pass in. So we get these nice accessor functions if we call these macros, as we saw in Aura attribute set.h. I called gameplay attribute property getter. This is going to generate the getter for the health attribute, not its numerical value, but an object of type fGameplay attribute, which is contained within that attribute data. So why don't we go ahead and follow what the attribute set header recommends, and that is to create this attribute accessors macro. Let's go ahead and copy these lines, and back in our Aura attribute set at the top, underneath all the includes, we'll go ahead and paste them. We need to delete these stars, the asterisks that came from that multi-line comment. And now we have this attribute accessors macro. And if we call this, then we don't have to use all 4 of these. So just under health, I'm going to replace this with attribute accessors here. Now hovering over, it says ability system component is incomplete. That means we're going to have to include it here in the header file. There's no way to get around that. So I'm going to go into Aura attribute set.cpp up at the top where I've included ability system component. I'm just going to go ahead and Control X to cut that out. And we're going to include it right here in the attribute set. That way we can use these macros. So the attribute accessors thing is just another one of those boilerplate things that you're going to add to your attributes. And because of this, we can now use those accessor functions. For example, if I want to initialize health to, say, a value of 100, I can go into my constructor and use init health and pass in 100. And even though I didn't create an init health function, I used my attribute accessors macro, which calls these 4 macros, one of which creates the initter, and by default, that's called init health. So I can use that to init the health, but how do we see that change? How can we verify that it's working? Well, we can compile and launch the editor. I'm just going to go ahead and run in debug mode. And right here in the editor, I can press play, I can click in the viewport, and I'm going to hit the tilde key to bring up the console, and I'm going to type the console command show debug, that's one word, ability system, that's also one word, so 2 words total, show debug ability system. Now this brings up a debug view for the ability system, and it has a lot of information. It shows attributes for avatar, BP, aura character. See, so we know that our avatar actor has been set correctly to BP aura character. It says authority, that means we're looking at the authority version. Now there are no other client machines, so the only version there is the authority version. And we see for owner, BP, or a player state. So it knows that our avatar actor is the character and our owner actor is the player state. That's all thanks to calling init ability actor info. We see in red showing debug for BP or a character. Press page up and page down to cycle between targets. So if we press page up, we can cycle to other targets. And we see the name change right here. It says showing debug for BP Goblin Slingshot C1, but we can cycle back around to aura character. It shows some other information. It shows the name of the computer. That's my computer's name. And it actually has the location and rotation right here. You can see it update as I'm moving around. We have an instigator and an owner for our ability system component. We see the controller is BP or a player controller, and the pawn is BP or a character. So it knows a lot of this information. And beneath all that, we see owned tags. We're going to look at that as soon as we get into gameplay tags. And yet underneath all of that, we see the 4 attributes here. We have health, followed by 100. That's what we initialized it to. And then max health, mana, and max mana, the other attributes. And we didn't initialize those. So show debug ability system is a great way to sort of debug some of our attribute values and also see what gameplay tags our character has. So that's a nice way that we can do some debug. I'm going to go ahead and close out of the editor. And now we've added some boilerplate here that we can reuse for all of our attributes by using the attribute accessors. And that gives us these functions we can use to initialize and set. Now, I'll give you a bit of a spoiler. The constructor is too early to call the setter. That's why we have the emitter here. But now we have this attribute accessors, which we could use with all of our attributes. So here's what your quest will be for this video. You're going to use that attribute accessors macro on the other attributes. So go ahead and add that. That way you'll have those accessor functions. And once you have those, you can now give initial values to debug ability values have been set. I'm going to be nice and late max health for this one, changing it to mana. And finally, we have max mana accessors for the init mana, 50, hot debugging or successfully, and it's looking good. Boilerplate that it simply creates. Use those functions as those we have accessors. So great, see you soon. Right here, row. And if we also sets the current value, base and current. So it's using so we can take a look at these, the attribute, that fgameplay attribute data, the value, the setter for, and then add a game specific. It says this go to declaration or usages. You can just when way to get around that. So I'm going to go into Aura attribute set.cpp up at the top where I've included ability system component. I'm just going to go ahead and control X to cut that out, and we're going to include it right here in the attribute set. That way we can use these macros. Welcome. In this video, we're going to make an actor that can change our attributes. We'll often want some sort of object in our world that we can pick up that will affect our attributes in some way. So I'd like to have an actor that's sort of generic all-purpose that we can use that has the inherent capability of changing attributes. Now, we already know that the preferred way to change an attribute is through a gameplay effect, but we haven't learned how to create and use gameplay effects just yet. So we're going to make an actor that will change an attribute directly, and we'll see the limitations of doing it that way, and we'll create a sort of to-do, basically add a comment that says we plan on changing our system to use gameplay effects in the near future. So let's make a new actor class. I'm going to go ahead and launch the editor, and we'll make a new C++ class. So I'm going to go into C++ classes, Aura, public, and right-click and make a new C++ class, and this is going to simply be an actor. Welcome. In this video, we're going to make an actor that can change our attributes. We'll often want some sort of object in our world that we can pick up that will affect our attributes in some way. So I'd like to have an actor that's sort of generic all-purpose that we can use that has the inherent capability of changing attributes. Now, we already know that the preferred way to change an attribute is through a gameplay effect, but we haven't learned how to create and use gameplay effects just yet. So we're going to make an actor that will change an attribute directly, and we'll see the limitations of doing it that way, and we'll create a sort of to-do, basically add a comment that says we plan on changing our system to use gameplay effects in the near future. So let's make a new actor class. I'm going to go ahead and launch the editor, and we'll make a new C++ class. So I'm going to go into C++ classes, Aura, public, and right-click and make a new C++ class, and this is going to simply be an actor. I'm going to click next, and I'll put this in its own folder called actor. Now, this will be a sort of generic class that will apply some sort of effect. So I'm going to call this Aura effect actor. And create the class. I'll go ahead and close the editor and open up my new actor here in Writer. So here's aura effect actor.cpp, and I'll go ahead and open up the header file as well. Here we go, and I'll drag them over to the left here. Now, Aura Effect Actor is going to be pretty simple. We'll make this much more versatile in the future, but for now, I just want to be able to overlap with Aura Effect Actor and apply some kind of attribute change. So for now, I'm going to remove the tick function. I'm going to remove the comments that we get here by default. And in the CPP file, I'll remove the tick function here and remove these comments as well. And because we don't need to tick, I'm going to set this to false. Primary actor tick, B can never tick. No ticking behavior, at least so far. Now, Aura Effect Actor needs some kind of overlap volume. I'm going to opt for a sphere, and this will be a private variable. So I'll make a private section and add a T object pointer of type useSphereComponent. We'll go ahead and add a forward declaration for that, thanks to Writer for the shorthand, and this will be called simply sphere. And I'll give it a U property with visible anywhere, and that's all we need for now. Let's go ahead and construct it. So here in the constructor, we'll say sphere equals. I'll use create default subobject, specifying useSphereComponent, and thanks Writer for the auto include there. And the native name will be simply sphere. And we can make the sphere the root component, or we can attach it to the root. Either one is fine. I think what I'd like to do is have a static mesh as the root and attach the sphere to it. So we can go back to the header file and we can add a static mesh component. This can be a TObject pointer of type use static mesh component, and we'll call this simply mesh and make this also visible anywhere. So we can go back and construct us also visible anywhere. So we can go back mesh and make this also visible anywhere. So we can go back and construct our mesh. Since I'd like to make the mesh the root, I'm going to put it above the sphere. So I'll say mesh equals, we'll use create default subobject with use static mesh component this time, and call this simply mesh. And we'll set the mesh as the root. So we'll say set root component, mesh, and we'll attach the sphere to the root. So we'll say sphere, setup attachment, get root component. That way, if the mesh moves, the sphere moves with it. Now we just need a overlap function to call when sphere overlaps with some other actor, and we'll go ahead and make an end overlap function as well. And this is all stuff you should be familiar with. We'll make the overlap function as well. And this is all stuff you should be familiar with. We'll make the overlap functions, and they can be public. We're going to make a virtual function. It's going to be void. We'll call it simply onOverlap. Now, the onOverlap function signature needs to have a number of input parameters to make this function bindable to onComponentBeginOverlap on the sphere. And I'll quickly show you how to figure out what those input parameters should be. But first, we're going to add them. We're going to say uPrimitiveComponent. That's the first one. That's a pointer called overlapped component. We have an A actor called other actor. Another uPrimitiveComponent called other comp. An int32 called other body index. a bool called B from sweep, and a const f hit result. Reference called sweep result. And this must be a u function, so we'll add the u function there. And this is a function we can bind to on component begin overlap. So we'll generate the function. Here's the definition. And we'll bind this to on component begin overlap on our sphere, which we must do in begin play. So we're going to say sphere on component begin overlap dot add dynamic, as this is a dynamic multicast delegate. We pass in the user object and the callback function, which will be the address of a or a effect actor on overlap. So this is the basic way to have a callback function fired off in response to something overlapping with our sphere component. And I mentioned I'd tell you how I knew this function signature. If you don't know how to figure that out on some kind of delegate, you can right click and go to the definition of that delegate. We see here on component begin overlap belongs to primitive component, and this is its type. We can go to the definition belongs to definition that belongs to definition of out on some kind of delegate. You can right click and go to the definition of that delegate. We see here on component begin overlap belongs to primitive component, and this is its type. We can go to the definition of this, and we see that it's created here with declared dynamic multicast sparse delegate, and this delegate of type f component begin overlap signature is defined using this macro. And here we see the input parameters required for any callback that will be bound to this delegate. And here's f component end overlap signature, the delegate for end overlap events. If we want to bind a function to that, then here's the list of input parameters that a callback must have to bind to this type of delegate. And primitive component has one called on component end overlap. So we can copy these parameters and we can make our end overlap function here in Aura effect actor. So we're going to make a virtual void function called end overlap. And I'm going to paste in those input parameters. Now in the declare delegate macro, the type is separated. Now function lab function, so we can copy primitive component have to bind to. Here's the list of input parameters that a callback must have to bind to this type of delegate, and primitive component has one called on component end overlap. So we can copy these parameters and we can make our end overlap function here in Aura effect actor. So we're going to make a virtual void function called end overlap. And I'm going to paste in those input parameters now in the declare delegate macro. The type is separated from the variable name. And the first two here are u primitive components and on component end overlap. These first two called overlaps with these bound to a given delegate. So we'll be seeing more and more of the be making for any trick that you can. We can see what that signature should be. So this is kind of a, for any function that can be custom delivers work between a pair of callbacks to derive. So let's go ahead and generate the end overlap to this end overlap. We can hover over and see that this is add dynamic or for actors. that have overlap volumes that you want to trigger off some kind of function call in response to overlaps. This is all very much boilerplate, right? We call this boilerplate because it has to be done if you want an actor that can overlap something. Now for actually defining what to do when we overlap, that's what we really want to figure out here is what do we do when we overlap with something? Now, we'd like to change the value of one of the attributes in the attribute set for Aura, but we know that to do that, we should be really applying gameplay effects, and that's why we call this effect actor. But until we learn how to do that, we're just going to change a value, such as the health attribute on Aura, and that will give us the opportunity to learn how we can access Aura's attribute set and her attributes. But we'll also learn how this is a very limited approach that restricts us in a lot of ways. We don't have a lot of freedom and flexibility. So first, let's learn how we can access the other actor's ability system component on overlap. Since we have access to the other actor, the actor that overlapped with this particular sphere component, we can see if that other actor has an ability system component. Remember, in the owner actors where we constructed our ability system component, we made sure to implement a specific interface related to the ability system. If we go to, say, the player folder in the public folder here, Aura player state, we see that we made sure the Aura player state is derived from iAbilitySystem interface, and that interface has a pure virtual function, getAbilitySystem component. Now, this is very nice because we can take any actor and see if it implements this interface. And if it does, we can get the ability system component that belongs to that actor. So we really don't have to care what type that actor is, whether it's a character, a pawn, or just an actor. If it implements the interface, we can call getAbilitySystem component on it. So here in onOverlap, what I'd like to do is take the other actor and cast it to an iAbilitySystem interface. So I'm going to make a local iAbilitySystem interface pointer called ASC interface, for lack of a better name. And I'm going to cast to iAbilitySystem interface the other actor itself. And I can wrap this in an if statement. I can say if this doesn't return a null pointer, then ASC interface will exist within the scope of this if statement. And what I can do here, since I have the interface, is I can find the attribute set. Now, I know that Aura attribute set has a health attribute. So I can find an attribute set on this ability system component of that type if it has one. Now, this is a very limited approach. Again, once we use gameplay effects, we won't have to care what the type of the attribute set is if we want to change some sort of value of an attribute. But for now, until we learn better ways to do it, we're going to learn how to get that attribute set from the ability system. So what we do first is we take the interface, which we know implements the pure virtual function getAbilitySystem component. Now, we can assume that that ability system component will be a valid pointer. So far in our game, we haven't implemented this function on any actors that should return a null pointer, if we call it. So I'm not going to bother checking it to see if it's null. And from the ability system component, I'm going to call getAttributeSet. Now, getAttributeSet is a function that requires a t-subclass of based on uAttributeSet. A t-subclass of is a u class that we can specify so that the ability system component knows which type of attribute set to look for if it has one. So we want to search for uAuroAttributeSet. That's the class of the attribute set. So we can use uAuroAttributeSet static class, which will satisfy this input of type t-subclass of. So this whole expression here is going to return an object of type uAttributeSet. So because this returns a uAttributeSet, we are going to want to cast to uAuroAttributeSet. So I'm going to wrap this all in a cast. We're going to say cast to uAuroAttributeSet, and we'll wrap this up. And we can store all of this in a local uAuroAttributeSet pointer called AuroAttributeSet. And this has to be const because getAttributeSet returns a const uAttributeSet. So we'll add const to this. And now we have the other actor's AuroAttributeSet, if it has one. Now, in our game, all of our actors that implement the ability system interface have an AuroAttributeSet. So we know that this should be a valid pointer. In this case, I'm not going to bother checking if that is null. I'm just going to take AuroAttributeSet, and we're going to do something. Now, notice we have access to health, mana, get health, get mana. We have these attributes which are public, and those attribute accessors, thanks to the boilerplate attribute accessors macro. So we can set these values. I'm going to call setHealth. And setHealth requires a float. Well, I can get the AuroAttributeSet and call getHealth, and I can add some value. I'm just going to hard code a value, say 25.f. Now, we see the red squiggles here because, well, this is a const uAuroAttributeSet, so we can't really change things if it's a const. For our protection, this is something that the ability system enforces. We shouldn't be setting the health directly on the AuroAttributeSet like this. The AuroAttributeSet should either set its own attribute values or have those attributes changed in response to gameplay effects. So already we're doing something that we shouldn't be, but since this is for learning purposes only, before we fix this up to have a better design, we're going to break the rules a bit just so we can set that health value and see it change. So I'm going to go ahead and give myself a semicolon here that I was missing for this line. And AuroAttributeSet, since it's const, well, I'm going to cast away the constness of AuroAttributeSet. Now, this is kind of a big no-no in programming. It's not something that you want to be in the habit of doing, but we're going to do this with a big fat to-do to change this to a better system. So before I break the rules, I'm going to add a to-do comment here that says, change this to apply a gameplay effect. For now, using const cast as a hack. So we got this big fat comment telling us that we're, doing something we shouldn't be doing and that we have it to do to change it. So what we're going to do is create a UAura attribute set and set it equal to the result of a const cast. We're const casting to type UAura attribute set. And because we're using const cast, we need the asterisk here. And what we're casting is aura attribute set. And we're going to call this mutable aura attribute set. And we're going to use mutable aura attribute set to call set health. So we have a const pointer. You're not supposed to change const pointers, but if you want to break that rule, we have the power in C++ to do that. This is something you should use extreme caution with. All we're doing is breaking encapsulation here, and throughout this course, we're going to make sure to maintain proper encapsulation and good coding practices. But as we would like to simply see the value change, we're going to cast away the constantness of this pointer so that we can mutate it. And of course, once we learn about gameplay effects, which is going to be very soon, we're going to instead have this function apply a gameplay effect, and we'll see the benefits of that. So we now have a function for on overlap that will take the health on the attribute set of the actor that overlap with it and set it equal to its own health plus 25. And we won't bother with an end overlap implementation just yet. All we're going to do here is if we do this, we'll go ahead and destroy the effect actor itself. So we're just going to call destroy here. And now we just want to test this out and overlap with it in the world and see our health value change. And that's going to be your quest. I would like you to create a value change out and overlap overlap implementation just yet. All we're going to do here is if we do this, we'll go ahead and destroy the effect actor itself. So we can overlap with it in the world. And see our health value change. And that's going to be your quest. I would like you to create a health potion. So create a blueprint based on our aura effect actor. You can call it BP health potion if you like, and set its static mesh. Look for the potion bottle static mesh in our assets folder. And you can set that. And then test with show DO and conquer this. I'd like to make a blueprint, so I'm going to go ahead and I'm going to go to my blueprints folder and make a new folder here. And print actor. And I'll make a new blueprint class and I'll search for aura effect actor. And choose that. And I potion bottle here, big. And there's my potion bottle. And I can see that it looks open this actor blueprint and choose that. So we'll place our actors in here. And I'll make a new and search for potion. Bottle. Here it is. And there's my potion bottle. And I can see that it looks a bit too big. I'm going to drag one into the world and see how big. Yes, it is too big. So I'm just going to scale it down here. I'm going to multiply the mesh by 0.2 for the scale. Now I'm going to multiply the mesh by point. So I'm just going to scale it down to the world and see, you can see that for potion bottle, here it is, and there's my potion bottle, and I can see that big. Yes, it is too big. So I'm just going to scale it down here. I'm going to multiply the mesh by 0.2 for the scale. Now that's of course going to scale the sphere down, so I just need to increase that sphere radius there. And now that I have a health, I need to increase that. Now that's of course going to scale. And now that I have a health potion, increase that sphere radius there. And now that I have a health potion, I can test this out in the world. I'm going to save all first and press play. And hitting the tilde key, I can type show debug ability system to see the value of my health. And if I ability system, to see the value of my welcome itself. Now that we know what attributes are, it's so I'm going to use that. Now, so we haven't created and construct up gameplay attribute. One of the few sort of meticulous things in the gas system that we have to deal with. Okay, so now we have 4 attributes in our attribute set, and that's great. So great job. I'll see you in the next video. And getting started here, but don't system. Now this brings up a debug view for the ability system. And it has a lot. Now this word, so 2 words, that's 1 word. The console command show debug, that's 1 word. Ability system, that's also 1 word. So 2 words total, show debug, ability system. Now this brings up a debug those accessor functions. For example, if I want to initialize health, to say a value of 100, I can go into my constructor and use init health and pass in 100. And even though I didn't create an init health function, I used my attribute accessors macro, which calls these 4 macros, one of which creates the initter, and by default, that's called init health. So I can use that to init the health, but how do we see that change? How can we verify that it's working? Well, we can compile and launch the editor. I'm just going to go ahead and run in debug mode. And right here in the editor, I can press play, I can click in the viewport, and I'm going to hit the the tilde key to bring up the console, and I'm going to type the console command show debug, that's one word, ability system, that's also one word, so 2 words total, show debug ability system. Now, Now, this brings up a debug view for the ability system, and it has a lot of This is something that the value change. So pause the video. System to see the value of my health, and if I run up to the potion, I pick it up, and my health is now 1. And 25 to the potion, I pick it up, and my health is now now 125. So our health potion is increasing our health by 25 as expected. Perfect. So we now know how we can access the ability system for any actor, and we can access the attribute set of an actor with get attribute set if we pass in the T subclass of or the U class for the type of attribute set we'd like to find on that ability system component. And get attribute set returns a const pointer to that attribute set, and we learned that we could sort of bludgeon our way past that constness by casting it away with const cast. Now, you should know that const cast is not something you want to use as a matter of habit. It's something that you can use if you don't quite know yet how you're going to do what you want to do, but you're trying to figure out ways to make things work. It's one of those ways that you can break the rules to get things working, but seeing this in your code should be a reason to sit and kind of try to think of a different solution that can allow you to not violate the constness of your code base. And in our case, we made a very blaring comment to tell us that we do plan on removing the requirement to const cast. In fact, that's not really the biggest problem here. The biggest problem is that our aura effect actor is very, very specific. It changes the health by 25. Something like effect actor should be able to apply any effect to any attribute in any number of ways. It should be versatile and reusable and shouldn't have to violate the constness of any pointers. And that's going to be what we end up doing here. So that's why we have it to do. For now, we know that we can access and change attributes for our health. And so far, we can only see that change by showing the debug information for our ability system. But in an actual game, we're going to want some HUD elements. We want a UI with health bars and icons and things that show us what's going on. And so we're going to want to set up a nice system for seeing our health. And we'll do that in the next section. So great job, and I'll see you soon. Welcome. So our game project involves attributes, such as health, and in nearly all game projects, health and other important attributes are displayed to the player on the screen. We refer to objects displayed on the screen as widgets. And in Unreal, we create widget blueprints to provide visual representations of game data. Widget blueprints are derived from the base C++ class user_widget. Widget blueprints need to receive data. A health bar needs to know how much health to display. An icon for a given ability needs to show the correct icon for that ability. The point is that widget objects must receive data so they know the correct values to depict. And the game is rife with this data. The attributes set contains numerical data for all of the attributes belonging to a given character. The player state might contain a number of variables that need to be shown to the player on the screen for any number of reasons. There are numerous classes in the game, each containing data that may or may not need to be known by the widget objects in order to show the player what's happening behind the scenes of the game mathematically. So the question arises, how should the widget object get that data? There are a number of ways. The widget object could manage to dig its hands deep into the game code, retrieving pointers and references to the characters, controllers, player states, ability system components, attribute sets, and access all that data it needs directly. But is this the best way? As you're making your game project, the question should arise in your mind, how should this type of system be designed? As the game grows in size and complexity, how should this type of data be handled? How would, say, an experienced developer do it? How do AAA games do it? That's what we're concerned with in this course, how to do this in a scalable and maintainable manner. Now, in a well-structured program, we should have a separation of concerns. With UI, we have 3 different domains. The first domain is the display of visual effects of the data, such as health bars and ability icons, basically all your widgets. We'll call this domain the view, as it contains all the things the player views while playing the game. Now, we also have the data itself. These are the numerical values, the player's health, the player's level, mana, experience, which abilities have been unlocked, what their levels are, and what buttons those abilities are assigned to. All this data exists within the codebase of the game project itself, and we'll call this data the model, as it models the underlying rules and results of the game. This is the data that will ultimately drive the widgets that we will see in the view domain. Now, getting data from the model to the view is a task we need to think about. This can be done in a number of ways, but a good way to organize this is to have some sort of class that can handle retrieving the data from the model and broadcasting it to the view. This class can be responsible not only for the retrieval of the data, but any calculations or algorithmic functionality involved in processing that data. Retrieving the data from is to have some sort of class that can handle organize this is to have some sort of class that can handle retrieving the data from the model and broadcasting it to the view. This class can be responsible not only for the retrieval of the data, but any calculations or algorithmic functionality involved in processing that data. This class exists in a domain that we'll call the controller in this system, and the controller will be responsible for retrieving data from the model and passing it to the view so it can depict data visually. Now, we're not talking about the A controller or A player controller classes in the engine. Those are designed to possess and control pawns. What we're talking is a controller class used to drive data to the view. So for that reason, we'll refer to this as a widget controller. This means the view can simply focus on how the data should look, receiving the data from any broadcasts made from the controller. But the view may contain widgets that the player can interact with, such as buttons. When the player clicks a button, that action may result in some change in the model, such as increasing attributes or granting new abilities to the player. So the controller's job is also to facilitate the actions resulting from the widget interaction by the player, causing changes in the model. In other words, the controller is a middleman between the view and the model. Now, some implementations of this software architecture pattern are different than others. Sometimes the widget controller is only responsible for retrieving data from the model and presenting it to the view. But for our project, the widget controller is going to have a little bit more responsibility in that it'll handle button presses and information that the player will provide and actually send signals out to the model so the model can make changes. With the model view controller architecture, we have 3 separate concerns, and each domain is isolated from the others. Which makes the system highly modular. It prevents us from hard-coding dependencies that would render the system rigid. Our model shouldn't ever need to care about which controllers or widgets are being used to represent their data. It's the controller itself that depends on the classes in the model. The controller should never need to know which widgets are receiving data broadcast to them. It's the widgets that depend on the controller. And if we maintain these one-way dependencies, then the model can have its widget controller changed out for other widget controllers without needing to change any code in the classes in the model. Likewise, the controller shouldn't need to know what types of widgets the system has, as it's the widget that depend on the controller. This way, the controllers can have their widgets switched out as well, without changing any code in the controller. And now we have a code base that's flexible and well-coded. This is the type of system we'll design for this game project. And we'll see the benefits of such a system as our project grows in complexity. Our controller can be a simple U object, and we'll give it the ability to harvest data from the system and broadcast it to the widget. And we'll create a subclass of the user widget that will be compatible with our widget controller class. So our next steps are to create this architecture for the UI in our game. We'll want our own apps are to create compatible with our widget controller class. So our next steps are to create this architecture for the UI in our game. We'll want our own custom-based widget class, which we'll call U or a user widget. We'll make the widget controller class U or a widget controller, and we'll want to subclass the HUD as well, so we can have a location where these classes can be constructed and initialized. Once we have the system in place, we can go about harvesting and broadcasting data in the widget controller, receiving it in the widgets we create that can display visuals in the view, and we'll be able to see the health and mana attributes in our game. So we'll do these things next.